my hope in this 90 minutes is to give you as much bang for your buck as I can in terms of overviewing what is known for learning undirected, discrete graphical models with a few pointers to various other directions. And in the last maybe 20 minutes or so, I'm going to outline what I view as an important direction for future research on which there's been almost no work at all. So even if you're an expert already in graphical models, but you want a direction to work in, then this could be one possible direction. Great. Now, in the spirit of boot camp, I'm going to assume that you know virtually nothing, which is clearly not going to be the case for the majority of you, but you can entertain yourself while I go through some basics. So, all right, so I'm going to start by motivating graphical models by giving a couple sort of high-level scenarios where one could use graphical models fruitfully. Then I will talk about learning graphical models, like what this problem even is, two versions, parameter estimation, structure learning, and we'll go into some details in each of those. Okay, so one scenario where people have used graphical models is in medical diagnosis. The idea is somebody comes into the ER, their chest hurts, they have chest pain. Now, oftentimes it's the case that they have heartburn, but sometimes they have a heart attack. Obviously, you'd like to figure out which of these is the case. So you make some measurements, maybe heart rate. They report that they're tired or something, a few other things. And the goal is to figure out what is the likelihood of each of these given the data that you've seen. Okay, now a graphical model will tell you how these variables are related in a sort of compact way that is then useful for computing these quantities of interest. What's the likelihood that it's heartburn? What's the likelihood that it's a heart attack? Okay. Another scenario where one might want to use graphical model is in a recommendation system. So here you have a bunch of items. User has rated some items. Let's say they've liked all of these items. You'd like to find what is the likelihood that they're going to buy this other item if I recommend it to them. And a priori, it's not so clear how to do that. If you have a bunch of data over users and items, then one could potentially learn the joint distribution of preferences over these items as described by a graphical model, which would then allow computing posterior probabilities, like what's the probability that I'm going to buy the latest Justin Bieber album? Or what's the probability I'm going to buy these speakers? Okay, now often you actually care about these probabilities, not just is the person going to buy it or not. Because even if this probability is way lower, the speakers are $2,000, so you'd probably recommend that if there's a reasonable chance of the person buying them. All right, so graphical models from the very beginning. We'll use P to denote the dimensions. So we have P random variables, x1 through xp. Each of those is a vertex in a graph. So there is some graph here. Now, the graph structure encodes the statistical dependencies or conditional independence relationships amongst the random variables. So in particular, every vertex xi will be conditionally independent of all the other vertices or all the other variables given the set of vertices or variables at the neighbors. Okay, and we'll use this partial I to mean the neighbors of I, and that will appear again and again and again. It's like boundary set. Okay, and also we have this sort of compact notation. Xi is conditionally independent of xa given x partial I, or the neighbors of I. Okay, now it's a classical fact that for non-negative probability distributions that satisfy this sort of Markov property, they factorize into a product over potentials, where there's one potential for each clique. You could take maximal cliques if you wish instead. This is the Hammersley-Clifford theorem. Now, certainly one can check, if I'm going slow and you forgot some of the basics, you can check that a factorization structure of this form, where you have a product over cliques in the graph, implies all of the associated Markov properties in the graph. So that's pretty easy to check. The other direction is a little bit more technical. There's some Mobius inversion and so forth. Okay, good. So what's the point of these graphical models? What's so great about them? Well, in many applications, you want to compute posteriors of this form, just like in the two examples where I gave you. And the graph structure helps you do this. People have developed a variety of algorithms that sort of work on these models that use the graph structure, and then it helps. It helps do this computation efficiently. In general, these sort of computations are not so easy to do. Okay, so that's not the subject of what I'm going to talk about, but we have a bunch of talks in this workshop on this, including Ahmed's talk on local algorithms and amenable graphs, Alex's talk on tensor PCA, Christina's talk on tensor completion, and perhaps others that I've missed. So sorry if I've missed your talks. But many problems can be formulated in this sort of general setup, compute a posterior. Okay, and if you're a student here and you want to know more, then you should take 6438, which I'll be co-teaching this fall with Greg Warnell. A little advertisement. That entire course pretty much is about how do you compute these sorts of posteriors. Okay, yeah, so please visit the course. All right, what's the point of this bootcamp talk? Well, in many applications, we don't actually have the graph structure. We don't have the model at all. All we have is a whole bunch of data. And what you would really like is to learn the graphical model that describes the data. Okay, so that's what this talk is about. So the question is, given data, how do you estimate the model? Well, there are two criteria for whether my algorithm is doing a good job. The first is, what's the sample complexity? How much data do I actually need? Data is expensive. It's often limited. How much of it do I need? Second question is computational complexity. So how does the runtime for a theoretician scale asymptotically with p, the dimension, the number of variables, and n, the number of samples? And in general, the sort of modern applications where this is interesting is p is very big, so you would like to have a low runtime. Okay, so these are the two driving performance criteria to understand this question, and I'll illustrate sort of what's known in this context. Okay, so before I go there are two high-level questions. Like, what it is that we're even trying to do? We say estimate the model. Well, the first thing you could try to do is learn the parameters or the graph structure, assuming that there is such a graph structure. These models are very flexible, and they sort of naturally describe physical systems with locally interacting components. And so oftentimes it will be a good assumption that there is a true model, and you'd like to learn it. For instance, if you have some biological network of some sort, there's some meaning to what is this structure? Is this edge there or not? And well, can we learn that structure? Can you learn the parameters that say what the strength of friendship between these two people are, or whatever the case, right? So these things have intrinsic meaning sometimes, but in the examples that I outlined, often you don't care at all about the actual presence of an edge or non-edge. What you really want is to make predictions using the model. You want to compute these posteriors. Okay, and there's been like almost no work on that. I should say that this list of references is extremely incomplete, and there's little, sort of many others there that are in each of these just to cover the thousands of other papers on this topic that I haven't been able to include on the slide. But these are more or less the only papers that have studied how do I learn a model? If I don't care about the model, all I want is for these posterior probabilities that are computed using the model to be accurate. And so this is a somewhat different question. It's analogous to studying prediction error and linear regression as opposed to parameter recovery. And so it's a sort of classical notion at the high level, but has not been investigated significantly in the graphical models context. Okay, so yeah, I'll tell you a little bit about this last bit of work at the end, or towards the end. Okay, I'm going to focus on binary pairwise models, which are also called Ising models, after a person named Ising who worked on them. So what is the situation here? Well, each of the variables is binary. That's a natural model for all sorts of systems of interest, like, dislike, spin up, spin down, neurons firing or not, and so forth. Now, the idea is that each of these pairs of particles or variables or spins are interacting in some local way. There's some force. They interact with the ones that are close. And the strength of that interaction is according to some parameter. We'll say theta ij between variable I and variable j. Right? So if theta is very positive, these things want to be aligned. Maybe you like the same movies as your friends or something. If theta ij is negative, then they prefer to be anti-aligned. Maybe you prefer not to go to the same events as your sworn enemy or something like this. This was whether you attend a given event. This is a social network. You'd want to potentially have negative weights. Now, from these local interactions that describe how things agree locally, one describes a probability distribution over an entire collection of variables, as I've described. And concretely, the distribution is written like this. And this is called also a Gibbs measure. But don't worry about the name if you haven't heard about it. And specifically for Ising models, the interactions are pairwise. So that means a given variable decides whether to be plus or minus by sort of separately aggregating the information from each of its neighbors as opposed to jointly looking at all of its neighbors at once. So like, what does that really mean? I'll give an example. So suppose that we have a social network, and this is like, do people attend a given event? So I might have a friend, and if they go to the party, I'm more likely to go to the party. There's some other friend, and well, they're my friend. If they're going to the party, more likely to go to the party. But if they both go, I know that they're just going to spend the whole night arguing, and it really sucks to be there, so I'm definitely not going to go. Okay, so now I can't just consider each of them individually. I have to consider them jointly. So that would be a three-wise interaction, which is not captured in a pairwise model. Okay, so the Ising model is just separately looking at each of these, and it sort of weights my likelihood of attending the party given each of my friends. All right, we're going to assume that each of these edge parameters, theta ij, is lower bounded by some constant alpha, upper bounded by beta. Obviously, alpha could be 0 and beta could be infinite, and then there's no restriction on the magnitude of the interactions. These alphas and betas appear again and again. I'm not going to worry too much about the node-wise parameter. This introduces a bias at each node, so you can ignore it if you want. And yeah, like I said on the initial slide, this sort of distribution satisfies the Markov property. Okay, due to the factorization structure. This is a product of pairwise potentials. All right. I should also say, any questions, please ask. I don't have like a particular set of stuff that I absolutely have to get to. So if you take up a few minutes with questions, that's time well spent. There's almost certainly, like many other people, have your same question. So yeah, please ask. Yeah, and also probably there's some notation that's just going to be outright wrong. So yeah, you should definitely just ask if there's something that's confusing. Yeah, please. Thank you. That's super useful already that you asked this question, because I was about to forget that. Yeah, so we're going to assume pretty much throughout the whole talk that the neighborhood sets are of size upper bounded by D. So D is the maximum degree. Thank you so much for the question. Yeah, any other questions?
So the historical perspective of Ising was lattice, like playing magnetic mechanism. So you didn't have a network structure, you have a lattice structure, the nearest neighbor.
Yeah, exactly. So these models were initially there to study spontaneous magnetization, phase transitions, and systems. How do you infer the network structure? That's the whole point. Yeah, so exactly. So in statistical physics, you might just have an understanding that the spins are arranged on a three-dimensional lattice or a two-dimensional lattice. And so you know the model. The whole point is that in many of these modern applications, you have no idea what the model is. You observe data from the model. And we'll see a formalization of that. OK, so before we get to the learning question, one of the nice things about these graphical models is that aside from helping with inference tasks like computing posteriors, they allow you to even represent a high-dimensional probability distribution. So we can do a quick calculation. We have an arbitrary binary distribution. Then there are 2 to the p different probabilities. And so you need to put those in a table, -1, but to leading order, right? And on the other hand, if we have p independent random variables, and they're binary, you just need to encode the bias, the Bernoulli parameter for each one. And so then it's very easy to represent the joint distribution. It's just p table entries. And if we have a graphical model with the maximum degree bounded by d, so you have this sort of sparsity in the graph structure, then it's a nice but very easy exercise for you to check that, again, it's linear in p number of table entries. So you inherit the efficiency of representation that one has in the independent case. But of course, this sort of model is much more useful because the variables are actually related to one another, unlike in the independent case. So computing a posterior given some information that you've observed is actually a useful thing to do. OK. I mean, if people want to ask about the calculation, you can ask me after in the coffee break or something. I mean, it's a simple calculation. It's more fun to leave it to you, but yeah. Okay. D is a constant, exactly. Okay, so the naive bound here has like 2 to the D or something. So yeah, you'd want to assume that D is a constant. Okay, good. So finally, the outline of this talk in detail. Okay, we're going to talk about parameter estimation in Ising models when you know the graph structure. Sometimes you might know the graph structure. Like if you're, I don't know, if you're Facebook or something, maybe you just outright know who's friends with whom. But you want to figure out how strong are these interactions between people. So that's a natural setting. And we'll see most of the details of analysis of logistic regression for getting parameter estimate in a known graph. Next, we'll consider the situation where you have no idea what the structure is. And we'll look at 3 different algorithms. One of them is sort of a brute force search. We'll see that maybe that's not so good for Ising models. There's something better that one can do. And then finally, we'll consider the case of trees. And I might do trees first, just because trees is particularly simple. Okay, and then finally, like I said multiple times, we'll talk about learning for predictions when you have no desire to learn the actual structure. You just want to learn a model that's pretty good as far as computing these posteriors. Caveat, many important topics are omitted. Latent variable models, I will not touch on at all. I'm going to assume that all of the variables are observed, which in practice is certainly not the case in most applications. But yeah, there's a body of work that I won't touch on. Gaussian graphical models I won't really say much about except for one slide to make some comparisons. Caroline will talk a little bit about, or maybe a lot, about Gaussian graphical models in the afternoon. And a question, yeah. Good. So yeah, the question was, does D, the upper bound on the number of neighbors, affect the structure learning task? Yes, very much so. D is bigger, the problem's harder, significantly, and we'll get into the details there. Yeah. Okay. Good. So part 1, parameter estimation. You know the graph. You want to estimate the parameters. So here's our situation. There might be some bigger graph that I'm not drawing. Now, the starting point for the natural way to think about this is just to write down the conditional distribution of a node. So we're just going to focus on some particular node. We're going to look at the conditional distribution of a node given all of its, not just its neighbors, all the rest of the nodes, period. But because of the Markov property, we know that we can replace all the rest of the nodes by the neighboring nodes, because the rest of them are conditionally independent given the neighbors. Okay, so we can just write out this conditional probability. And now, using the factorization structure of the joint distribution here, you get a whole heck of a lot of cancellations, which lead to this quite simple form, which just involves stuff that is adjacent to node I. Okay, so this is a sum over j in the neighborhood of I, theta ij xj, plus theta I. And then here's the same thing, and then here's with a negative, corresponding to xi being negative 1 there. Okay, now this is just the logistic function that we all know and love, the sigmoid. And we'll just remember that sigma is this sigmoid function, the logistic function. Okay, so why is this useful, or how can this be useful for estimating the parameters? Well, if you want to estimate the parameters adjacent to node I, the ones that are involved in this conditional distribution, well, let me change notation on you a little bit just to reduce the presence of subscripts. So the node of interest, the one that we're looking at the posterior of, we're going to call Y. All the neighbors with a 1 here, we're going to call Z. And then I realized last night, didn't have time to change it. All the parameters that are involved with node Y, we're going to call beta here. Yeah, we used beta before as the upper bound on theta ij. So just for the next, 5-10 minutes, beta has a totally different meaning. Forget about these upper bounds on theta ij. And then we'll go back to beta. I'll remind you. So for now, beta is just the parameter. It's just like you've probably seen in linear regression. All right, so with this notation, we have the probability that y is equal to little y given z. So, okay, we get, with xi being -1, we get a minus inside the sigmoid just because it's 1 minus the thing. You can write that out. And then, okay, so now we can compactify both of these and just write the probability that y is equal to little y, where little y is +1 or -1, is equal to sigma of 2y beta transpose z. Okay, good. So that's the conditional distribution of y, given that you've observed z. You're trying to guess what y is. So sort of the thing that every statistician would try as a first attempt would be to maximize the likelihood. And so we can write the negative log likelihood that's suitably normalized of our entire data set. So we have y1 through n and z1 through zn. If we just realize that this is a product over the different samples, because all of the samples are assumed to be IID. And then we write the sigmoid, which I guess is sitting here for us for convenience. We take the log of this, and we get the minus cancels from the denominator. And we have exactly this quantity inside here. Now, W is the parameter that you're trying to compute. What's the likelihood of the data if W was the true beta parameter? And so W is appearing here instead of beta. Okay, now the prescription in general in this sort of scenario is to maximize the likelihood. So let's choose beta hat to be argument of the negative log likelihood of this likelihood function. And classical stats, you could look in van der Waart, for instance, would tell you that you have asymptotic normality that root n times beta hat minus beta converges in distribution to a multivariate normal with the Fisher information matrix sitting inside there. Okay, so this is classical stuff. Just to emphasize again, we know the graph structure. We wrote down the posterior of the node given its neighbors. There are d neighbors, so we're just sitting here in d dimensions. D is assumed to be fixed. D is like 20. Now you're scaling the number of samples to infinity, and one has this sort of statement. Okay. So, sorry, yeah? Oh, yeah, sorry. Okay, sorry. So yeah, I absorbed the theta I. I didn't want to have to carry this theta I separately. And so because we have plus theta I or minus theta I, when we take beta transpose z, this 1 in theta I is just going to give us this theta I, and the x neighbors of I, theta neighbors of I gives you this term. Thanks for the question. Yeah. Any other questions? Okay. Okay, so you expect beta hat minus beta to be roughly of size 1 over root n. But this distributional sort of statement doesn't exactly tell you that. And so we'll see how does one get finite sample bounds on this. And what I'm going to describe is some sort of complicated amalgamation of what's in these papers and as well as Philippe's course notes here. So you're invited to check those out if you want the missing details. And any mistakes here are purely my own. Good. Now, I should say, of course, that what all of these do is in the sparse case, here there's no sparsity, and that's somehow the point of knowing already the graph structure. So if you know the graph structure, well, you're just trying to find the parameters to the neighbors, and you know who the neighbors are. There's just no sparsity. So this is just vanilla logistic regression, but we'll see that the steps taken here, or maybe we won't see, but I'll claim that later, that the steps taken here work also in the sparse case, and I'll say what's different. Alrighty, good. So we're gonna try to analyze this. We're gonna try to get a statement of this form: beta hat minus beta is equal to roughly 1 over root n with high probability. Everybody good? Yeah.
You chose a particular y or xi to use here, and then wrote everything in terms of the posterior for that. If you had chosen a different xi, you would have a loss function or a likelihood function over some of the same theta ij parameters. Like, does it matter which one you choose? Do you use all of them at once to
Yeah, that's a great question. What people tend to do, I think, is just sort of arbitrarily choose one of them, right? Because both endpoints of the edge are going to have that theta ij present. How do you choose which? Like, you get a different estimate from each end. Yeah, it sort of doesn't matter. I mean, as long as your guarantee on the thetas is strong enough, then they're both just going to be accurate. One could probably cook up some scenario where it does matter, but yeah, at least a little bit. But yeah, good. Any other questions? Okay. Got all sorts of hazards here. There's like a hole over. If I fall into the hole, then somebody will have to like pull me out. Okay. Good. So we're going to try to analyze this logistic regression. We get this beta hat from maximizing the likelihood. So how good is beta hat? Okay. Now there are a bunch of ways to think about this. They actually matter in subtle ways, and I'll tell you one particular way that gives optimal rates. And there are other ways, but they require different tricks. So there's some subtleties here. Somehow the mechanics of like compiling this and going line to line ends up not being so hard, but then like really thinking through what's going on might take a little time. So hopefully it's not too confusing. All right, so here's our here's our loss function, L of W. It's random because it's, remember, based on the data that's given to us. There's this true beta. We don't know what true beta is, but we have beta hat, and beta hat is the minimum of this loss function, the negative log likelihood. Now we want to somehow argue that beta hat is close to beta. So here's one way to do that. So the first step is to Taylor expand the loss function around this point, beta. Okay, so then we get L of beta plus delta. This is our perturbation. So we get the actual point plus the first order term plus the error term. So this delta L here is just the error term. It's not anything else. It's sort of reusing the notation with L, but it's the error at capital delta. Okay, so this is just a Taylor expansion. Haven't really done anything. Okay, now the next two steps, we're going to try to bound certain quantities. So the first step, we're going to bound the magnitude of this first order term from above. So let's just get a first little step in that direction. So here we have this inner product. We use Holder's inequality to get the L1 norm times the L infinity norm, L1 norm of delta, L infinity of the gradient. Now L1, L2 norm, you convert here to the 2 norm of delta. You get a factor root d, which is a constant for us, so who cares? And we still have this infinity norm of the gradient at the true point, the true parameter beta. Okay. Next step, lower bound the error term. So that's this error term in the Taylor expansion. Okay. Now this will require some pretty serious computation, and I won't go into all the details of that, but I'll sketch a couple of the ideas. Finally, so I mean, I should just say, what does this actually mean? So we know that the loss function is convex. I should have emphasized that, so you can actually carry out the optimization efficiently. And it's strongly convex if one has a quadratic lower bound in some neighborhood of that point, and it's strongly convex around beta. And quadratic lower bound can be written like this with some kappa. Okay, now suppose that we've carried out steps 2 and 3. What does that buy us? Well, if this remainder term is bigger than the magnitude of this first order term, right? That's bigger than this, then we know that the loss at beta plus delta is bigger than the loss at beta, which tells us that beta plus delta could not possibly have been the minimizer of the loss function because it's not the minimum. Okay, so that's the logic. And beta hat being the minimum, if we write it as beta plus delta, delta here now is the error relative to beta, then we immediately conclude that just from rearranging this inequality, that the error is bounded like so. So root d, infinity norm of the gradient, divided by this kappa, which is the strong convexity parameter. Okay, so So this is essentially the set of steps that are taken in these guys' paper, Vifre, Misra, and Lokov, I guess. And without any sparsity because we know the structure, okay? So you can look at their paper to see some of the details, some of the gory details, but I'll describe some of these computations that are easy to do. Okay, so we need to bound this infinity norm of the gradient. We need to lower bound the strong convexity parameter, and we see that we just immediately get bound on how far we are in the parameter, in the 2 norm. Okay. So we'll start with step 2. Let's bound the gradient. Okay, so here's our loss function. If you take a partial derivative, this goes to the denominator, the minus 2y zj pops out if we're differentiating with respect to wj. A calculation, this is a nice little exercise, shows that the mean of each of these terms, even conditional on z, is 0. That's not so obvious, but it's true. And now we have a sum of n mean 0 terms, and with a little bit of effort to bound the magnitude and stuff, it's not so much effort. This is sort of very clearly nicely bounded. One can just apply Hufting's inequality to get a bound on the infinity norm of the gradient by just controlling each of these, right? The maximum of each of those. Okay, so that's the calculation. For the next term, we're trying to get a lower bound here on this error term. And essentially, we're just going to, yeah. Oh, yeah. So good. So a priori, you'd want this to be D. I wrote P here just because you might want to get the parameters in the entire model. So even though you're doing some local regression, you still have P squared variable, or P edges in total. Yeah, no, it's a good point. Yeah, I won't go into detail enough in terms of exactly the bound that it will matter here, but yeah. Yeah, if all you care about is the single set of parameters adjacent to a node, then there is no P somehow in the whole problem. And so this would be D. Yeah, it's a good question. Okay, good. So we're trying to approximate this error term from below. So we should compute the Hessian. So you take an extra derivative here with respect to Wi. Or sorry, wk or something, a different index. The computation gives you this, where we have the entire matrix being the sum of these outer products over the samples. And each of these terms, if we look at it, so yi is plus or minus 1. Each of these is plus or minus 1. And so what's living inside of here, I should have put a beta inside there. So what's living inside of there is basically a sum of the beta I terms with a 2. And so one can convince yourself that sort of we lose at most a factor of e to the minus 2 L1 norm of beta if we were to just eliminate this factor in front. And this is great. So this is our sort of lower bound on the Hessian. And now's the part that's kind of admittedly very sketchy because it would sort of take the rest of the time to go through the calculations in detail, and they're very nicely presented in the Los Alamos guys' paper. So I won't go into the gory details, but intuitively at least, if we're trying to bound this error term, we can just take the first order of this, which would be the second order in the whole expression in the whole Taylor series. So we have this delta quadratic form with the Hessian living inside of there. So when we go to this expression, we now have this factor in front that we had and an empirical variance along direction delta. And there's some very nice steps to actually get this lower bound, where kappa now is exactly e to the minus constant times beta 1. Okay. For those of you who have seen analysis of regression, this is essentially like a restricted eigenvalue or an incoherence condition on the design matrix described by Z. Yeah, I won't say more in that direction. Okay, good. So what do we have? We have this. We have this. Right, these bounds on the gradient, bounds on the restricted strong convexity parameter. We can go back and we can plug it in to our estimate on beta, and we get this rate. Woohoo! Okay, so that's the upshot. This is sort of non-sparse logistic regression analysis. The L2 error in our estimate beta hat is roughly going like 1 over root n, with some extra dependencies on the magnitude of the parameters and the dimension. Good. So here we assume that D was constant, the dimension or the number of neighbors. I'll just give a reference to some really interesting results about logistic regression in the high dimensional case, where one still exactly is just doing maximum likelihood. So Pragyasur and Candes have some sort of a series of papers understanding how things look in that regime. So you should look if you're interested. So high dimensional logistic regression with no regularizing or anything like that. Okay, so this is going to conclude the parameter estimation part. We have a guarantee. It's quite reasonable. One can actually get lower bounds that essentially match this. So this is sort of the right answer. And we can move on to structure learning. Okay. Good. Question, please.
Just a comment. In the previous one, maybe you want to comment on the fact that the only place where it's actually easing model learning is this lower bound over there, right? So the last inequality, everything else is standard logistic regression.
Yeah, that's a great point.
The only place where you're using the easing model.
Yeah, it's true. Yeah. So I buried the only place where it actually matters that's an easing model. Yeah. Plus minus one and the sort of the strength of the interactions that, yeah, so, yeah, it's true. Yeah. Yeah, everything else is just standard logistic regression. So. Good. Okay, so let's move on to structure learning. We don't know the structure in many practical situations. So what can you do? Well, we need to learn the structure from the data. So how do we do that? Well, we're going to talk about trees briefly because it's very classical and nice, and it sort of started this whole field. We'll talk about a search algorithm and understand why in some settings it's optimal. And then we'll revisit logistic regression where now you don't know the structure and one has to regularize. All right, so here's our structure learning problem. We have our graph, bounded degree by D. We have an easing model on the graph. The variables are binary, p dimensions, or p variables. And again, we have our alpha and beta bounds on the theta ij. So you can forget about beta being the parameter in logistic regression. This is what beta is now. It's the upper bound on the magnitudes of the theta ij's. So we observe a bunch of data, n samples. Each of these samples is a full p-dimensional binary vector. They're IID samples. What we want to do is learn the graph and estimate the parameters from the data successfully with high probability. Okay, so we already saw how to estimate the parameters if you know the graph. So we can focus on the first question. How do you estimate the graph? And like I said, we'll start with tree graphical models. So we're going to do all of this in the situation where the graphical model was a tree to begin with. Okay, so one method that was proposed way back in 1968 was to maximize the likelihood. I mean, maximizing the likelihood wasn't proposed in 1968, but you know what I mean. Okay, so we're going to maximize the likelihood of the data, right? We have our data set, choose the tree structured graphical model to maximize the likelihood, minimize the KL from the empirical distribution is the same thing, and a brief calculation that I'll also leave as a pleasant exercise for you is to show that the best choice of parameters that have a tree support, in other words, the theta ij's that are non-zero form a tree structure, one minimizes the KL or maximizes the likelihood by minimizing negative of the sum of the empirical mutual informations across the edges in the tree, in the support of the theta. Plus, there's a bunch of terms here that don't actually care about the structure. Okay, so what Chaolu observed, and this is pretty much the majority of their paper, they made the observation that computing the maximum likelihood tree, maximum likelihood theta with the tree structure, is the same as minimizing the sum of mutual informations over the tree. And this is good because this can be done efficiently. So how come? Well, the maximum likelihood tree is the max weight spanning tree where each edge is this empirical mutual information. And we can use, for instance, Kruskal's algorithm or Prim's algorithm or other algorithms. Kruskal's algorithm tells you the following. It says you should greedily add edges. First, the biggest edge, biggest meaning maximum empirical mutual information. And then you should go on to the next highest edge. You should add that. You should keep going, keep adding edges greedily according to empirical mutual information, unless by chance you wish to add an edge that closes a cycle. And then, well, it's a tree. We know that we don't have any cycles, so throw those edges away and keep going. And eventually you'll have a spanning tree. And that is the maximum likelihood tree structure. Okay, so that's classical stuff. It was a few years later that this method was shown to be consistent for discrete distributions. So as this number of samples goes to infinity, you actually recover the true tree. In the context of the Ising model, I couldn't find any written analysis, so I'm writing my name here as well as Mina Karzand, but it's not a terribly hard lemma, so I called it a lemma, and it's probably known, but maybe it's sort of folklore. So the question is, when is this the right tree for an Ising model? So here are some actual bounds. So here's a situation. We have an Ising model with alpha and beta, lower bound and upper bound on the parameters. If the number of samples is this big, constant, e to the 2 beta divided by alpha squared log p, then with high probability, the Chaolu tree is the correct tree. And this is tight in the minimax sense up to a constant. So if one has fewer than a constant times the same number of samples, then with high probability, any estimator will make an error. Okay, so this is the sample complexity of recovering an Ising model on a tree. And it sort of tells us how hard this problem is. One thing that's maybe an obvious observation is that the degree of the tree appears nowhere. It's a tree, and it doesn't matter what its shape is. One just has e to the 2 beta living up here. Okay. Do I want to sketch this? Yeah, I'll sketch the proof because it's yeah.
You know what happens in that critical window?
Oh, that's a good question. So I know that Anima and co-authors have derived error exponents for this, but I don't think anybody has understood what really happens in the critical window. Yeah. Although, we might be able to. We should chat in 20 minutes because some of the things I'll say at the end I think tell us some of the stuff that's happening. One can actually get pretty tight controls on what the errors of the Chaolu algorithm look like. Yeah. Yeah, and even this next slide will give us some insight into what the errors that Chaolu makes look like. Okay, so what are we trying to do? We're trying to say if we have blah number of samples, then Chaolu tree is like the correct tree. All right? So it turns out that like the case of interest to understand this question is this tiny little 3-node graph with a strong edge. Beta, remember, is the maximum edge strength. I'm writing here hyperbolic tangent of beta as the correlation between the endpoints. We're assuming for the purposes here that the node-wise fields are 0. And one can just do a quick calculation to check that the correlation across an edge, if ij is in the edge set, then the correlation is the hyperbolic tangent of the parameter. So our situation is that we have these 3 nodes. There's some interaction between 1 and 2 that leads to a correlation of mu. And there is the maximum possible interaction between 2 and 3, which leads to a correlation of tanh beta. All right, so when does Chalu mess up? Well, Chalu messes up if mu 1, 3 hat, the empirical correlation here, which is monotonically related to the mutual information. So I'm just looking at empirical correlations instead of empirical mutual informations. So Chalu messes up if this edge, which doesn't show up, appears to be stronger than this edge, which is the true edge, okay? Which this happens if the empirical quantities are ordered sort of in the reversed way. Now, each of the empirical quantities is close by epsilon to the true quantity, where epsilon is 2 over n log p with the square root. This is just Hufting's inequality. So these quantities are pretty close to the true ones. And so we can understand what this situation is that causes Chalu to make a mistake. All right, so mu 1, 3 empirical is bigger than mu 1, 2 empirical. That implies that mu times hyperbolic tangent of beta, that's the true mu 1, 3, is the product of the correlations across the edges, plus epsilon is at least mu minus epsilon, because this is mu 1, 2, and the smallest that it could be, the empirical, under this concentration event. And if we solve for mu, that tells us that mu is less than 2 epsilon over 1 minus tanh beta. Okay, so again, to remind you, this is sort of one particular toy example, but it turns out to be the sort of crux situation for the Chalu algorithm. And just by this quick computation, we see that Chalu algorithm is going to make a mistake if mu is less, or with decent probability, if mu is less than 2 epsilon over this quantity. And returning to this picture, what this really means is that this edge is super strong, and this edge is super weak. Now, if this edge was so strong that it was just have a correlation of 1, then 2, 1, and 1, 3 are effectively the same, right? Because 2 and 3 are always going to take the same value. And so in that situation, I mean, it's truly non-identifiable. You just have no clue whether 1, 3, or 1, 2 is the true edge. And in fact, it doesn't mean anything. And so this is kind of approaching that situation where you don't have enough data to distinguish these 2 very close quantities. Okay, so this is a condition on mu. You can define an edge to be strong if mu is bigger than this quantity. And there's a slight improvement that one can get with a square root in the denominator that I won't get into. And the basic lemma is that strong edges are recovered, because then the correlations are ordered appropriately. Okay, now to get the full statement, one has to consider sort of arbitrary incorrect edges that are added in the graph and consider the cycle that connects to the endpoints and so forth. So a little bit of thought, but probably everybody here could fill in the details themselves, or you can look in our paper that I think is appearing this year, or appeared, I'm not sure. Okay, so this is an analysis of Chalu algorithm, and I won't go back, but it proves the sample complexity that I stated. Good, okay, so done with trees. What can we say about general graphs with bounded degree? So we're back to our scenario here. We have some Ising model. It's not a tree anymore. We observe data, want to learn the graph, and estimate the parameters. But of course, we already did that, so let's not worry about estimating parameters. Okay, so a baseline sort of algorithm appeared in this paper of mine with Elchanan Mosel and Alan Sly, more than a decade ago at this point. And the algorithm is very simple, and it'll set us sort of a baseline for maybe how to think about this problem. I will say that this algorithm works for general Markov random fields, not just for Ising models, and that will be important in a couple of minutes. Okay, so what's this algorithm? We're again just going to check for every node. We're going to try to find the neighborhood. Okay? And the basic idea is to use the Markov structure that's implied by the graph structure, the Markov property that's implied by the graph structure. So we're going to test for a candidate neighborhood set U, whether it's contained in the neighborhood set. Okay? So we're going to do this test. I'm going to describe the test. We're going to see that it sort of lets U pass if it genuinely is a subset of the neighborhood set. It fails if U is not a subset of the neighborhood set. And then, of course, we could choose the biggest passing set to get the true neighborhood set. So that's kind of how the algorithm will work. How do we do this sort of test? So imagine that U is not a subset of the set of neighbors, right? So here's some node that's not a neighbor. Well, if you take that node, and now you condition on the rest of the neighbors, so that's this W, then changing the value of J does nothing to node I because of the conditional independence. This can be tested from the empirical distribution, so you could put hats here, but the true distribution will satisfy this with exact equality, that this is equal to 0, that flipping the value of node J does nothing. So U fails the test if it is not a subset of I, where the test is search over W, try all the values of J and U, and flip it and see if it changes the posterior at I. Okay, now suppose that U is a subset. Then for every J in U and W that contains the rest of the neighbors, flipping the value at J, assuming the Markov random field is non-degenerate in a certain sense, should change the value at node I. And again, one can sort of replace the true distribution by the empirical quantity, but for convenience, I've just written the true thing. And one can bound the change here in terms of the parameters of the model. That makes sense? So this is, I mean, how one chooses this W and so forth, there's a little bit more stuff involved. One does a search also over W's, and there's a certain minimum or a maximum there. So there's some quantifiers to actually make this search formal, but it's clear that if one chooses W like this, then one gets this inequality. Okay, so if U is a subset, passes the test, what's the algorithm? Well, for each node, test all the possible neighborhoods, choose the largest U passing the test. This takes time, P choose D. You've done this for every neighborhood. And the theorem says that this works. And that's great. Okay, so this works. So the sample complexity here, I neglected to write the dependence on alpha, but it's over alpha squared. The main term here is e to the 4 beta d log p. And then it takes time p to the 2d plus 1 because of this search over neighborhoods. Good, so this is, we'll see in the next slide, it's a good thing because this sample complexity is actually essentially optimal. This is a depressing thing because p to the 2d plus 1 is actually not a fast runtime, and one would like to have better runtimes. Okay, so for, I don't know, maybe a decade or 15 years, there was vigorous activity in trying to understand how to improve the runtime, and at this point, this is pretty much understood, and I'll describe what's known. Before we get there, I'll make a remark about the sample complexity. Okay, so Santhanam and Wainwright have the following argument that tells you you need this many samples. If you don't have this many samples, you're in trouble. So what's the argument? Well, take a degree D clique, so D plus 1 clique, put all the edges equal to beta, so they're all just maximum. Let's look at the posterior probability of a given node given all of its neighbors. So it has the sigmoid structure that we saw. Now, it is often the case when beta is reasonably big that there's sort of a low temperature situation that many of the variables are +1 or many of the variables are -1. And so in that situation, the posterior probability is going to be either close to 1 or close to 0. And you can now ask yourself the question, what happens if I just take an edge and remove it? Can one actually see that in the joint distribution? Or can one see that in this conditional distribution, in the behavior of a given node? And you can convince yourself that if I just removed one of these edges, then this quantity, which is what's inputted into the sigmoid to compute the posterior changes only relatively by a small amount. And we're way out here in either the left or the right tail in the typical scenario where this conditional probability is very flat. And so the conditional probability doesn't change very much if we slightly change the value here that is appearing in the sigmoid, which is what would happen if you deleted an edge. And so the intuition is that it's hard to detect deletion of an edge. And so it's hard to learn the structure if you don't have enough samples. And so the number of samples is lower bounded like this. And the true answer should have a squared here, by the way, but for whatever reason, their paper has this sort of thing when it has the dependence on degree and beta. Okay, so e to the beta d is a necessary term in the sample complexity. If the degree is getting big or if the maximum interaction is getting big, then it's hard to detect removal of an edge in a clique like this or in many cliques, and that gives us our lower bound. Okay. Good. So before I talk about a more efficient algorithm that improves on this, I want to make the claim that actually one can't improve on this if you want to learn general Markov random fields. And that statement is going to be pretty simple, and it's just going to follow by a simple observation that relates learning Markov random fields to a classical learning theory problem called learning parities with noise. So just out of curiosity, who's seen learning parities with noise before? Okay, great. Only a couple of people, or the people who have seen it are already asleep. Okay, so this is a very sort of clean, this is a very, very clean learning problem, and it's worth understanding because it has some conjectures associated with it that are interesting. So what is the learning problem? So now forget about learning graphical models. Okay, this is a learning problem. Let S be a random subset of size D out of the P total variables. You have no idea what S is. You observe n IID samples of the following form. X, which is just uniform on the hypercube, and Y, which is the parity of the X's in the set S. But sometimes you get an erroneous value for this parity. So with 10%, it flips. So you get all this data. You get n IID samples of this form. Your task is, hey, find the set. All right? So what can you do? Well, people have worked really, really hard to answer this question. And the best that people have come up with is searching over all of the sets S. And then there's sort of an obvious check if you want to check, is this particular set S the true one? Because the majority of the time, Y will equal the parity. And you can just see this from the data. And this requires time P to the D. Now, the conjecture is that that's as good as it gets. You can't improve this. And the observation that relates this to Markov random fields is that the joint distribution over X and Y genuinely is a Markov random field. So there is no significant thing that has to be said. The joint distribution is exactly described by a clique, a single potential that sort of enforces this parity constraint 90% of the time over the variables in S as well as Y. This is a Markov random field of degree D plus 1. And so then one gets that assuming the learning with parity with noise is hard, the same exact thing is true for Markov random fields. Now, the exhaustive search algorithm I described also solves general Markov random fields, and that's part of why it goes through all these complicated steps. And this is all just to say that the runtime of that algorithm is optimal under this learning theory assumption. Okay. Now, parity is this complicated higher order interaction. Ising models are simpler in the sense that they don't have these higher order interactions. And so the natural question is, are they easier? Are they easier to learn? Okay, so we're going to revisit logistic regression. This is going to largely follow sort of the work of Mark, Andre, and Siddhant. Possibly with permuted, they keep permuting their names every paper they write. So who knows? Maybe Andre's first, I think, on this one, but I don't know. So, okay, so what's the situation? We're just going to write down the conditional probability of our favorite node I that we want to find the parameters adjacent to being 1, given all the other nodes. And well, we already did exactly this thing before when we looked at the conditional probability where we knew the graph. Of course, now we don't know the graph, but still we can just write the entire vector of thetas that are adjacent to I against all the nodes, and that's what's showing up in the logistic function. Now, the theta here just has a bunch of zeros. Wherever we don't have a neighbor, if j is not a neighbor of I, then the corresponding entry of this theta I vector is just 0. So this is fine. It's exactly the same reasoning as before. We want to find the support of theta. That's the graph structure, the neighborhood set of I. So just as before, we can write the negative log likelihood. As I've emphasized here in the blue text, now theta is sparse. It has p dimensions instead of d. And the sort of modern canon of high-dimensional statistical theory tells us that we ought to consider m estimators for regularized loss functions, optimizing regularized loss functions. So we can minimize this loss function, which is exactly the same loss function we had in the dense case where we knew the graph structure, and add a regularizer, a penalty here, so lambda L1 norm W. Now, when this sort of situation is going to, when this sort of estimator, the best choice W here, is going to actually be close to the true parameter, when is theta hat going to be close to theta? Well, there's a theory that tells you when that is the case. And the general theory is called restricted strong convexity. And the idea is that we're going to follow exactly the same program that was outlined before for the dense logistic regression, where one has strong convexity and bounds on the gradient and so forth. So one goes through all of exactly the same stuff, except for now one doesn't need strong convexity in all directions because this regularizer sort of restricts the directions where the estimator can take values. And so one only needs strong convexity in certain directions. Now, that's useful because one doesn't actually have strong convexity in all directions. So this is true, whereas the previous analysis just straight up wouldn't apply in the high-dimensional setting. And for details, you should read through this list of papers. But I won't go into it in the remaining time. There's other stuff I want to get to. But I will state a quick theorem. And essentially what it says is that one has a nice bound also in this situation on the accuracy of the estimated parameter that looks much the same as the bound we had before in the dense case. Okay. Now, you might tell me, you're just estimating the parameter. We want to estimate the graph structure. What is this? So if we estimate the parameter accurately, you can convince yourself that if it's also the case that each of the minimum parameters is lower bounded by alpha, if you get each of the parameters quite accurately within, let's say, alpha over 2, then the non-edges will at most have a theta hat that's less than alpha over 2, and the edges will have a value bigger than alpha over 2. So one can convert accuracy of a parameter estimate into accuracy of the actual structure recovery. All right. Finally, I should just say that this optimization can be carried out in quadratic time as opposed to just using standard interior point methods. One can do coordinate-wise things. And the details are in this paper of Andre, Mark, and Siddhant. And of course, they're here. I should just emphasize, I've been sort of pointing it out at them, but they're here, so you should talk to them if you're interested in this stuff. There are many coffee breaks and so forth. Great. There's a lot more that can be said about discrete, general discrete models. I will not say anything more, except for to say that the two directions that one must generalize to understand general models are higher order interactions other than pairwise, and alpha bit size that's bigger than 2, so not just binary. And there are a number of papers on this topic, and Mark is going to talk on this topic in a couple of days, so you should attend his talk. Okay, there is also a parallel universe that addresses the Gaussian case instead of the Ising case, and there are indeed many parallels. So there are a sequence of papers that parallel the Ising model situation, although there are some things that are less well understood in the Gaussian setting than in the Ising model case. But there are some recent progresses in the Gaussian case that use sort of physical intuition that's analogous to situations in the Ising model to get nice results in the Gaussian setting. And Frederick Kohler, who's there, will be giving a talk on this topic, I think Wednesday, but I'm not 100% sure. Definitely in the next 3 days. So you should come to his talk. Okay. Good. So in the final 20 minutes that I have, I want to tell you about the problem that I think actually matters in most of these situations, which is we don't care about the graph. We just want to learn some model that has accurate posteriors because we're going to compute these posteriors. Okay? So here is our problem setup. It's exactly the same. We have an Ising model. Let's for now assume that the parameters are bounded below by alpha and up by beta. Same thing, n samples. Now you want to learn the graph and estimate, or learn, sorry, a graph and estimate parameters from the data in order that your Q, which I'm writing for your estimated distribution, the posterior computed using Q, is close to the true posterior. Or this eta here is the accuracy in the posterior. And in general, you might hope for this to be accurate, this posterior, for any node that you wish to compute the posterior of, and given any set of partial observations. Okay, so how many samples do you need is maybe the first basic question, and is there an efficient algorithm to do this task of learning the graph and estimating the parameters subject to this performance metric? That's the question. Okay, so a first thing that comes to mind for everybody I chat with is to say, well, let's try to get these posteriors accurate, but that's just the same as getting the whole distribution to be close. So let's just get some distribution that's close in total variation or KL or whatever. Maybe total variation makes the most sense. Let's make the learned distribution close in total variation. So who thinks that's a good idea? It's a pretty good idea, right? Okay, so it's not such a good idea, actually. I mean, it's sort of a good idea, but we'll see. Okay, so this is what we want. Learned distribution, learned posterior, posterior in the learned distribution is close to the true one. And you can convince yourself that roughly, if we're trying to get this sort of bound on the posteriors from a bound on the total variation, it requires the same bound. It requires the same quantity here, the same accuracy. So your total variation had better be less than eta if you want the posteriors to be less than eta. Now let's consider a simple example where P is just a product distribution. So it's the simplest possible thing. There are P Bernoulli parameters. We can ask how many samples do we need such that the total variation is less than eta. And it's an exercise in sort of, I don't know, minimax statistics to argue that this is the necessary and sufficient number of samples that one needs, P over eta squared. All right, so there's 1 over eta squared, but really the troubling part is P. So if I want to estimate a distribution that's close in TV and there are P dimensions, then I need P samples. In many situations, you just don't have P samples. So this is the sort of high dimensional setting that probably you've heard ad nauseum. N is much smaller than P. Yeah.
Maybe this is so far when you're learning graphical model, sample includes observations of all variables.
Yeah.
So which means that by definition each sample is p-dimensional.
Every sample is p-dimensional, exactly.
But now sort of you're changing your definition of samples.
No, sorry, I'm still sitting in that.
Still sitting in that.
Yeah, and this is still this is the sample complexity with each sample being p-dimensional. yeah, it's getting harder and harder to estimate the whole distribution to within a given total variation as the dimension grows. Yeah, so then you actually need more and more of each, you're getting more and more observations of each node. Yeah. Okay. Good, so the conclusion of this slide is that requiring the entire joint distribution to be close in any reasonable distance is just not possible in the high dimensional setting. So this is hopeless, so we should do something else. So to think about what the other thing we should do is, we should revisit a natural motivating scenario where we want to compute the posterior probabilities of the user liking each item, given some few items for which we have feedback. Okay? So we have some few items and we wish to compute the posterior given those items. And the key thing is that it's typically the situation that the set that we're conditioning on is pretty small. The user hasn't rated all of the items on Amazon because there are millions of items. So there are a few items that they've rated, and then you want to compute the posterior. So again, we want these posteriors conditioned on small sets to be accurate. And instead of the total variation, we can consider a local notion of total variation, where now the local total variation of order k between two distributions p and q is the supremum or the maximum over sets of size at most k of the total variation between the marginals on the set S. Okay, so this is just the total variation, but it's local because it's looking at all subsets of size k. You can convince yourself that it's still a metric, just like normal total variation. You can also just get immediately from Bayes' rule that, or even better, the definition of conditional probability that if this is small, then at least in expectation, the posterior probabilities of interest for sets where we're conditioning on small sets is also accurate. So this local total variation is actually the right thing to be looking at. And we can make our problem statement a little bit more precise by saying exactly the same things. You have a model, you observe data from it. Now you want to learn something that's close in this metric. Okay. Looks like. All right, so I'll give you a quick sketch of some of the ideas leading to the following two results. So, but we'll focus here on k equals 2. So we just want all pairwise marginals to be accurate. And some nice things happen when k equals 2. So in particular, in this 0 external field, so the theta I parameters were 0. The whole problem of this local total variation of order 2 being within eta can just be restated much more simply as asking that the correlations in the estimated model are within eta of the true correlations. Okay, so you observe data from some tree structured Ising model. You have some correlations in your learned model. You want those correlations to be close to the true ones. Simple enough. Okay, now I won't dwell on this minimax thing, but the first result is that one can efficiently learn a tree such that the accuracy of the correlations are bounded by this right-hand side with high probability. So this is the situation where we don't know the tree. The second statement is if the tree structure is known, then all we have to do is estimate the parameters so that the correlations computed using the model with the known tree, but the unknown estimated parameters is accurate. We get a root log p over n accuracy in the correlations. Okay, and this is optimal. Okay, so I should say at this point that the right answer somehow for this one should be the same as this one, but we don't know how to do this, and this is an open question. We're still thinking about it off and on, but it's maybe the most basic question in this direction that's unknown, the answer. But even with this result, there's still some kind of interesting observations that can be made. So I'll make those in the remaining few minutes. Yeah, exactly. This, in particular, so maybe it is worth dwelling on this slightly. So the main thing that one gets from looking at this is that there's no alpha dependence. So alpha is the weakest edge strength. If there are some super, super weak edges, then intuitively at least it shouldn't affect the posteriors that you're computing in the model. Because if they're super weak, you might as well put them at 0 and it doesn't change the distribution so much. And that's what this is saying. There is a dependence here on the maximum edge strength. Whereas if the tree structure is known, it doesn't matter how strong the edges are or how weak they are. The accuracy that one gets in the posteriors is only a function of the size of the model and the number of samples. And we don't have that sort of beta independence here. So yeah, it's a great question. So, okay. Good. So a little bit of review of tree structured easing models. If you've never seen tree structured easing models, then I'll state a few facts that are not review, but I will not explain them in great detail. But the first one is one that I already said before. So if we look at the correlation across an edge between two variables, that correlation is the hyperbolic tangent of the parameter. If one has a pair of variables that are separated by a path of length at least 2, so bigger than 1, then the correlation is the product of the correlations along that path that connects them. This is a nice exercise to just check yourself. Now, this is somehow the model that is the true one that's generating the samples, and we're going to estimate some other model with some parameters theta ij tilde that we chose. Now, the correlation across the edge in our learned model is just as here. It's the hyperbolic tangent. And the correlation across to other variables is, again, just as here. It's the product along the path in the learned model of the correlations in the learned model. Okay, so what's going to make this whole thing interesting is that it's often going to be the case that you just don't have enough data to learn the true structure. So then T tilde is some totally different tree than the true one, which means that the correlations between a pair of variables, like in this example, are computed along completely different paths. And still somehow one would like to say that these correlations are close to one another. All right. So the first question that I thought of is, oh, this is great. Let's just learn the tree. We know how to learn trees. This is just Chow Lu, right? So you could do that. So we know how to learn trees. This is I guess it got upgraded to a theorem, but it's the same lemma from before. It tells you if you have this many samples, then you're getting the correct tree. So now we can ask ourselves, if you have the correct tree, how much data do you need to guarantee that the correlations are close in the computed tree? So the first question, before we can even answer that, is what should you choose the parameters in the learned model? And the Chow Lu prescription is to choose the parameter in the learned model so that the correlation matches the empirical correlation across the edges. Okay, so that's a prescription that just says that's how you should choose those parameters. So you match, another way to say it is you're matching the moments on the edges. And a corollary of the previous result guaranteeing that you have the correct tree is that if your number of samples is at least, so we have the e to the 2 beta over alpha squared, that's from getting the correct tree. And we also have this 1 over eta squared, which is guaranteeing that given that you have the correct tree, that your correlations are accurate. So this second term is also needed if you want really accurate correlations. You might need even more samples than one needs for learning the tree. Okay. All right, so I'll just say a couple of words on even the case, why even the case where you know the tree and now you're trying to estimate the parameters is actually non-trivial, not so obvious. So what's going on? We're comparing correlations in the true tree from the learned model. I didn't mention what this notation was, but it's the information projection or whatever. It doesn't really matter. What matters is that this is this pi t p hat, that's just the distribution from your Chow-Liu algorithm. So that's just the learned distribution. So the error in correlation is between nodes W and W tilde is, here's the true correlation. We know that it's the product along the path in the tree. And we're in the situation where we have the correct tree, and so the estimated correlation is the product of the estimated correlations, the product of the empirical correlations. So we have these two quantities. Lemma says that if n is 1 over eta squared log p, then these quantities are close. And the issue is that each of these little steps has some error in it because it's estimated from the data. It's mu hat. And now the quantity of interest is the product of all of these. And so all these little errors add up. And so if you have variables that are pretty far apart, you are adding up errors along those paths, and it's not so clear how to control those errors. Now, it turns out that there's sort of a delicate trade-off that happens that exactly saves the day. And the intuition is that if these two variables are far apart and actually have a non-trivial correlation, then each of the correlations along that path have to be very, very strong, because otherwise they would have decayed. And if they're very, very strong, then one is in a sort of funny regime where the variance of those quantities is tiny, and one gets a huge boost in the accuracy of each of these estimates, which then means that even though they are adding up along this long path, each of the individual errors is tiny, and that compensates for the fact that they add up. Okay, so that's roughly how the reasoning goes there. But the point is that one is getting, in some sense, a dimension-free bound that doesn't care how far apart these are. And this gives us a first stab at what the sample complexity of this problem is. It's just copied down from before. All right, now this is annoying because alpha is showing up there. If the edges are weak, then it shouldn't make estimating these models so that posteriors are accurate. It shouldn't make that problem harder. So first thing you might try is, can we get rid of this alpha? And to that end, let's not try to learn the tree exactly. Let's try to learn something else. So a sort of idea that's present in many papers in the literature on learning tree-structured models of various forms in phylogenetics and other settings is to say, well, you know what, this edge, it's pretty weak. This is the same example roughly as before, except for, I'm assuming now, some concrete values, 0.9 and 0.02. So this edge is weak. The correlations in the true model are now 0.02 here and 0.018. And so these are close, and so we cannot be so confident that Chow-Liu is going to recover them correctly. So let's just ignore all those weak edges. Let's just get rid of everything that's weak that we can't be confident is going to be recovered correctly. This is the complement of what I defined as strong edges in the analysis of Chow-Liu. Okay, so instead of learning a tree, let's learn a forest. Let's ignore the weak edges. And one can argue that sort of the effective weak edges that you'd probably want to truncate at is exactly the accuracy eta, and this results in the following type of bound. Just e to the 2 beta over eta squared, which replaces this alpha by eta. Okay, so this is nice because it doesn't depend on alpha. It is not so nice because one can actually do much better by not caring as much that we learn the right trees. So at all, that we learn the tree that has any relationship to the true tree. And what I'll do is I'll just give some intuition for kind of the important scenario that illustrates what's going on, and the proof is a kind of complicated combinatorial extension of this simple model, this simple example. Okay, so here's what we have. It's the same example from before. We have a tree with correlation 0.9 here and 0.02 here between 1 and 2. As before, we saw that the correlation between 1 and 3 is close to the correlation between 1 and 2, right? 1 and 3 is just the product of the correlations along the edges, right? These are roughly the same, so Chow-Liu, you know, the empirical distribution might have a bigger correlation here, in which case Chow-Liu would learn the following tree, which is wrong. So we can ask ourselves, what is the set of all pairwise correlations in our estimated model that's here. So in our estimated model, the correlation between 1 and 2 is the product along these. Of course, in the forest where you just truncate these weak edges, the correlations here are 0 because there are no edges, there are no interactions. And so if we retain the true distribution, and here are all the pairwise correlations, here's the forest one, and here's the learned one, we see that the learned one is way closer. Because even though it doesn't get the correct edges, it roughly captures the global dependence structure. And one way to just see that is like I had said before, if 2 and 3 have such a strong edge that they're essentially the same variable, if their interaction is just 1, their correlation, then it sort of doesn't matter which of these two 1 is connected to. It just has to be connected to one of the things that's kind of varying together as a blob. Okay, so the upshot is that sometimes learning the wrong graph is way better than learning a graph only of edges that you're confident about. And that gives rise to an improved sample complexity, which has now the maximum of these terms instead of the product. So it can be as small as the square root of this quantity. And that's where we are at in this whole research direction. So I added this here because I very much hope that people will follow up on it. One other final remark in my final 30 seconds is, you might ask, okay, is this because our analysis kind of sucks, or is this because Chow-Lu sucks, right? And I should say that the correct answer just doesn't have this beta. Maybe that's a worthwhile exercise to think about. You can ask me why it's true. It's like a one-line answer, why the correct answer doesn't have this beta. Okay, so is it because Chow-Lu or is it because of our analysis? And so initially we thought it's our analysis, and we kept like hammering on Chow-Lu. It's actually Chow-Lu that's not so good. And here are just some plots showing how this local total variation is getting worse as you increase beta for the Chow-Lu tree. So there is dependence on beta, whereas the right thing should not have it. So one needs to come up with a better algorithm than Chow-Lu. Which I think is kind of cool because Chow-Lu is like the classical thing that everybody thinks about when learning trees. And what this is saying is that actually there's something else that we need to come up with if you care about computing posteriors, which is often what these sorts of models are used for. All right, so that's the proof. Whoa, that just went a little too fast, but I guess the conclusion is still up there. So to conclude, there's been a huge amount of progress in the last 5 to 10 years on learning discrete graphical models. I've shown you a portion of it. That situation is, I'd say for the most part, well understood. There are definitely a few questions left there, but its landscape is pretty well understood. And I think one of the important directions for going forward is this question of what if we don't want to learn the structure, we just want to learn the distribution that's close for what we want to use it for. And I'll end there. Thanks very much. Yes, please. That's a good question. Yeah, so the question is, can you have different models in general, using models with different parameters that actually give you the same distribution? And the answer is that there's sort of a bijection between the vector of all correlations and the vector of parameters, just in using models in general. And so you definitely would have a different distribution if you have a different set of parameters. But with that said, understanding sort of the topology of this space, like if you allow approximations, then the answer becomes highly non-obvious, right? So you could ask how close in this local total variation metric are two different models? And that's one of the questions that's sort of at the heart of this, yeah. Yes, please.
So you had the lower bound on the weights. Was that a lower bound on the absolute value, or was it just lower? Were theta positive or not?
Yeah, no restriction on theta being positive. Yeah, sorry. So the alpha beta was on the absolute value of theta ij. So exactly. It's just keeping the parameters away from 0. Yes, please. Yeah.
So it's kind of related question. So the way how I look at the identifiability or the uniqueness was from your talk was the stronger it is, the probably the more unique it will come out to be. But then sounds like the question that you answered for the lady sounds like depending on how you characterize it, you might not recover to the true structure. Is that the correct interpretation?
I'm not sure I entirely understood your question, but maybe I will just make one remark, which is using the last 3 words that you said. So that's probably not your question, but it's a different question. But definitely the sample complexity here for getting the posteriors or getting the correlations to be close is a smaller sample complexity than what is shown to be necessary for recovering the true structure. So there is a huge regime where it's just impossible. With high probability, you're going to get the wrong graph, but there's still a guarantee on getting the posteriors accurate. So I don't know if that answers your question. Sorry if it doesn't. Yes, please.
How easy can you use these algorithms for learning the structure in an online setting when you get more data? So initially you learn some structure, and then you get more data, and then you change the structure?
Yeah, that's a good question.
Can you update based on what you've computed so far, or you have to start from scratch all the time?
Yeah, I think you can update. I mean, I think a lot of these can be formulated as online learning algorithms, but it's something I've thought like extraordinarily little about. So other people in this room will definitely have more useful things to tell you. Yeah.
In the invited question, what is the one-line intuition for e to power 2 beta not being there?
Oh, yeah, okay. What is the intuition for e to 2 beta not being there, for beta dependence not being there? Okay, so one thing you could ask is how close is the true empirical distribution in pairwise correlations to the true distribution? And you know that it's going to be pretty close just by Hufting's inequality or something. And then you can ask, what happens if I search over all possible trees? And well, if I search over all possible trees and all parameters, then the true model is an example of a model that I'm searching over. And I know that it will have all of the correlations close to the empirical, because the empirical and the true one are close. And so then we just get the Hufting bound that tells you that like if you could just search over everything, then it would be there. So it's really a question about efficient algorithms. The sample complexity is sort of one-line argument. Yeah, great question. Yeah, thanks.
Some of the bound that you showed, like the number of samples, for example, that you need depends on how sparse the graph is.
That's right.
So how do you decide how sparse the graph should be for a given problem? You do it a priori?
Oh, but God tells me that. I mean, right? No, I mean, it's a good question. Yeah. How do you adaptively figure out the sparsity of the algorithm? Yeah, I'll admit it's something that I have intentionally avoided thinking about, and so I could mumble something, and it's probably not going to be the best answer. So, but I mean, this is like a whole theme in statistics, is how to come up with adaptive algorithms and stuff. Yeah, okay. So I'll leave it at that. But I mean, I would suggest asking our 3 friends from Los Alamos, because it's their algorithm and that achieves the best results right now, and they might have an answer that's specific to their algorithm.